So now we are going to look at a specific case of parity check codes, meaning low density parity check codes. So we have seen that parity check codes are very good, but they are not practical. What's the issue? So let's recap what we know. We know that the random parity check code has a minimum distance that grows linearly with n. So we saw that this minimum distance is approximately equal to delta times n. And this is what we call a good code. So this is actually a great property. And this is what we had. However, storing the parity check matrix will get an issue because we need quite a big memory to store the parity check matrix. The memory is n cubed. And we need to store all the positions of the matrix. We cannot compress them. So let's look at an example that is more or less practical. N equals 200,000. So it's 2 times 10 to the power 5. And the design rate RD is equal to 1/2. And then M is equal to 10 to the power 5. So it means that we need M times N memory cells for storing. So this is 2 times 10 to the power 5 times 10 to the power 5. This is equal to 2 times 10 to the power 10 bit that we need to store. So this is equal to 20 gigabit. So we need 20 gigabit to just store the matrix. This is approximately equal to 20 divided by 8. So let's say it's approximately equal to 3 gigabyte. We need 3 gigabyte of memory just to store this matrix of a sufficiently large n. And this is an n that is not so very far away from what is being used in practice today. So storing this matrix just is not feasible. So what we need is we need codes that share similar positive properties and have significantly lower memory complexity than the parity check codes. The low density parity check code come to the rescue. So low density parity check codes have been developed in the 1960s already by a guy called Bob Gallagher in his PhD thesis. So it was part of his PhD thesis was to analyze low density parity check codes and develop them because people realized that parity check codes cannot be practical. Then it turns out that this was a collaboration with Motorola. Motorola looked at this, they said, it's a pretty nice thing that you did there, but it's not practical either. So even these codes that you have developed, they are not practical. We cannot implement them. Let's not file a patent. That doesn't make sense. Nobody can use these codes. And then essentially the whole thing was forgotten until the late 1990s. So 25, 30 years ago. And then people rediscovered low density parity check codes and discovered that, these are pretty good. And actually with what the hardware we have today, this is easily decodable. No issue. So it always makes sense to look back and in the history of what has been done before to see maybe something that was deemed infeasible a few years ago, perfectly feasible because of Moore's law. The computing power increases rapidly, very rapidly. And this rediscovery of low density parity check codes was a big breakthrough, and essentially it was the foundation of what we call today modern coding theory. Modern coding theory essentially treats LDPC codes and variants of LDPC codes and analyzes the decoding of those. So what are the advantages of LDPC codes? First, can be shown, this is something that we do in the tutorial, or you have a tutorial exercise. They also have a good minimum distance, so they also share this behavior, which is, however, significantly more difficult to prove. Significantly. There is an exercise in the tutorial where you can go to the proof step by step as an exercise, but it's not trivial. There's also a small star on this exercise, which means it's beyond the scope of the material. But you can show it has good minimum distance. We are going to see that we have very, very simple iterative decoding schemes. Perfect. We can easily decode, and we have something that is a relatively low error floor. That's something we're going to see later. So it makes them feasible for operations at very low error rates, which the previous codes that were available in the 90s, the turbo codes, they couldn't do that. They had a very bad minimum distance, so they had error patterns that they couldn't correct, and they were not useful for low error rate applications. What is an LDPC code? It's a very, the main definition is very simple. The main definition says that it's a linear block code that has a sparse parity check matrix, which means that the number of ones is very small compared to the number of zeros. That means we can compress the parity check matrix efficiently. If the number of ones and the number of zeros is almost the same, compression is difficult. But if we only have a few number of ones, compression gets very simple. We can use zip to compress it, but we can also use more elaborate schemes. The first thing we're going to look at is the most basic class of LDPC codes that Gallagher already looked at. That's a so-called regular LDPC code. A regular LDPC code has a very simple definition. That's the following. So the regular LDPC code has two parameters, dv and dc. So we have two parameters, dv and dc. And regular LDPC code is a code where each column of H contains exactly dv ones, and each row of H contains exactly dc ones. And we assume that dv and dc are largely equivalent to 2. So every column has dc. C stands for column. No, sorry. My bad. So every column of H has dv ones. Why we don't use dc? Very good question. That will become later clear when we look at the graph representation. So dv is in the column and dc is in the row. dc stands for check, parity check equation. So we have each row of H corresponds to a check equation. So we have dc number of ones involved in this parity check. That's a regular LDPC code. And now, because the number of ones in H is small, the complexity of storing the parity check matrix is only O of n. So for instance, for each row, you can store just the number of the positions of the ones. And the position of the ones is independent of n because it's a constant. It's dv and dc. So it's independent of n, and therefore the memory complexity is only O of n. So let's take a look at an example. Here we have an example of a code with parameters 3 and 6. So we have a design rate of 1/2. N is equal to 18, M is equal to 9, dv equals 3, dc equals 6. And we can see that we have 3 ones in each column. So dv is equal to 3 ones in each column. And we have 6 ones in each row. 6 ones in each row. That's it. So that's a low density parity check code. And this code, well, its parity check matrix is not very sparse. So it has a density of 33%, meaning 33% of the entries are ones, 66 or 67% are equal to 0. So let's look at a larger matrix, so blowing up this matrix a little bit. So now, same parameters, 3 and 6. Now n is equal to 30, m is equal to 15. Still 6 ones per row and 3 ones per column. This is what you can verify. And for completeness, we just showed ones and we omit the zeros, so it's more clear visibly. So you can think of zeros everywhere else here. So I don't show these just for clearness. Now the density of the matrix is 20%, so it's decreasing. Let's blow up the matrix a little bit more. So parameters 3, 6, n equals 48, m equals 24. Again, we see 3 ones per column and 6 ones per row. Density is now 12.5%. Let's blow up more. Now we have n equals 300 and m equals 150. Parameters are 3, 6 again. Again, we have 3 ones per column. Now the ones are so tiny that they become points. But if you look at it, it's going to be 3 ones per column and 6 ones per row. It's going to be harder to verify, but you can believe me. And density is 2%. Can we go one more? Yeah, we can go one more. So now n is equal to 900, m is equal to 450, parameters are 3, 6, and the density is below 1%. So less than 1% of the parity check matrix are equal to ones. The rest are equal to zeros. Again, every column, 3 ones, every row, 6 ones. So that's an LDPC code. That's the simplest LDPC code. So we have some properties. First property is simple. We count the number of ones. So we can count the number of ones by looking at the columns or by looking at the rows. So we start by looking at the columns. So we have n columns, and each column has dv number of ones. So that's the number of ones. We have, we have m rows. We have m rows, and each row has so we have m rows, and each row essentially has dc number of ones. So the number of ones is m times dc. So we have this condition that n times dv must be equal to m times dc. So rearrange, say that m is equal to n times dv over dc. Now we can calculate the design rate of the code. We know the design rate is 1 minus m over n. Okay, so we insert m and n here. So it's 1 minus n times dv over n times dc. Cancel n. So the design rate is given by 1 minus dv over dc. That's the design rate of a regular LDPC code. So the parameters dv and dc uniquely determine the design rate of the code. So we immediately, when you see 3, 6, we had 3 dv equals 3, dc equals 6. Notice this is 1 minus 3 over 6, so it's 1/2. We can calculate the density. The density of the matrix is the number of ones, so it's n times dv, divided by the size of the matrix, which is n times m. So it's either dv over m or dc over n. Both are the same. And we can see that if n increases, the density approaches 0. Okay. Now, if the variable degree dv is even, then when we sum up all the rows of H, we have an all 0 row. So just summing up all of H means we have all 0. So there is at least one linearly independent row. So we can say that if dv is even, then the rank of H is upper bounded by m minus 1. We have at least one linearly dependent row in this case. But we can also show that with very high probability, the rate of the LDPC codes equals the design rate. If we calculate the probability that the rate times n is equal to the design rate times n plus nu, and nu is equal to 1 if dv is even, just to account for the fact that we have one linearly dependent row, and therefore this is equal to 1. So we know that the real rate is larger than the design rate, so we have the design rate times number of bits in the code plus 1. That's going to be the number of independent columns. So that approaches 1. So the probability that we have a full rate code also approaches 1 if n is sufficiently large, so if n goes to 0. So we just need to take into account that when dv is even, we have at least one linearly dependent row, but if n gets large, the probability is also larger. It just remains this one independent row. So how can we construct such a matrix? It seems to be difficult to construct because we have all these conditions that rows, columns, number of ones must be constructed. And Gallagher, he came up with a very nice way of choosing this, constructing the matrix using a banded structure. So, and the way of doing this is we divide the rows into dv sets. We divide the rows of H into dv sets with m divided by dv rows in each set. The first set of rows contains dc consecutive ones that we order from left to right across columns. Let's take a look at an example. Example here, dv. We have an example. We have dv equals 3 and dc equals 4. So what we do is in the first, and then we have m equals 9 and n equals 12. And the design rate of the code is 1/4. So 1 minus equal to 1 minus dv over dc. So 1 minus 3/4, 1/4. So what do we do? So first, we construct the first set. So we divide into sets that have m divided by dv. So 9 divided by 3, 3 rows. So in the first row, we have dc consecutive 1 from left to right. 4 ones from left to right. Then we go into the next row and put 4 ones. Then we go into the next row and put 4 ones. And then we have filled up our 3 rows in the first set. So we just put the ones next to each other. And then if we have used DC ones in every row, we go to the next row. And we go to the next row. So with this, every row has DC ones. And every column of the first set has a single one. Every column has a single one. So now how do we get the next set? Well, we just randomly permute this set and put it below. By having a random column permutation, every other set is essentially a random column permutation of the first set. By doing so, we make sure that every column here also has a single one and every row has DC ones. And then we repeat this until we have all our DV sets. And then we get the parity check matrix. That was Gallagher's method. It's not the best method to do, but because it has some drawbacks, but it's a good method to go for. Okay, so next, code construction by McKay and Neal. That's more the traditional one. So we start filling the columns of H, and we add a column with DV1s going from left to right. And we choose the position of the non-zero entries in each column randomly from the positions of the rows which have less than DC1s. When we reach the end, it may happen that we don't find enough such columns, and then we need to backtrack a little bit. Then we backtrack and see if we can fill some more columns. So here, if we want to fill column 11, then we have columns are 3 are 2, 4, 5, 6, and 9. And we can choose column 2, column 4, and column 5. And then we see that we have used all 4 positions. And then we have 3 columns left. Then the last column will choose this. Then we may need to backtrack a little bit, and then we get. I may also put a script for McKay and Neal construction. And later, when we look at irregular code, we're going to see an even simpler construction based on the graph of the code. Speaking of which, the next thing we're going to look at is the graph. And why we are going to look at the graph? Well, in principle, the MAP or maximum likelihood decoder that we have seen can be applied to LDPC codes. And unfortunately, this is not feasible because we have complexity of n cube on the binary radio channel and an exponential complexity in other channels. So it's infeasible in most channels. And the main success of LDPC code is because we have a very, 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 very simple decoding algorithm. And this very simple decoding algorithm is based on a graph. So we have an extremely simple graph-based decoding algorithm, which is suboptimal, but it gives extremely good performance that is getting us close to capacity. And this algorithm is based on the graphical representation of an LDPC code. That's the Tanner graph. Tanner graph is something that we're going to look at in the next video. So in the next video, we're going to look at Tanner graphs.